part 6, I want to talk about assessing development suitability based upon temperature related to solar aspect, slope steepness, and prevailing wind. This is a relationship that deals with the aspect of the sun relative to north, that is, for example, talking about a south-facing aspect, an easterly-facing aspect, a westerly-facing aspect, a northwesterly aspect, etc. So it is the position of the sun relative to north in the sky, and the angle of solar incidence with the land surface. Does the sun strike the surface of the earth at a perpendicular angle, wherein we have a much higher level of intense solar radiation intensity reaching the land surface, or does the sun's angle reach the surface of the land at a more acute angle with reduced solar radiational intensity? That has to do with the steepness of the slope. And then finally, we have prevailing wind direction. Wind tends to have a cooling influence, and so we need to be thinking about solar aspect. Where is the sun in the sky? What is the angle of incidence with the land surface? How steep is the land? And from which direction is the wind flowing? When we talk about solar aspect, the diagram immediately to the right begins to talk about the impact of a northerly aspect versus a southerly aspect. And we can see the southerly aspect on the right-hand side of the slide, where the sun is striking the surface of the earth quite directly. The whole slope is in full sun for a good bit of the day. That sun's angle of incidence with the land surface itself is quite perpendicular, so it's a very intense radiational input. In contrast, the north-facing slope never receives direct radiational input. All of the radiational input that the north-facing slope is indirect. It is from the influence of the south-facing slope warming adjacent air, and that adjacent warmed air then flowing into the north-facing slope to warm that area as well. And then in the lower right-hand side, we can see the effects then of the southerly aspect of a slope creating a hotter, sunnier condition versus the northerly aspect of the backside of the slope, creating a cooler, more shady condition. When we talk about east versus west aspect, we need to recognize that, at least in the northern hemisphere, the sun rises in the east and it sets in the west. And so when the sun rises in the east, it's striking these east-facing slopes. And one would say, oh, good, we're going to get the same effect on these east-facing slopes that we get on these south-facing slopes. Well, that's true. The sun behaves in a similar manner. It's just that the sun has been up for a much shorter period of time when it has a perpendicular angle of incidence with these east-facing slopes than when the sun reaches around and starts to impact a south-facing slope. In contrast, the sun has been in the atmosphere all day by the time it gets around to the westerly slopes. So if we have a situation where there's a steep westerly slope that's facing due west, the low-angled sun in the sky is going to create a high angle of incidence, and we're actually going to get quite warm conditions because the atmosphere is already warmed up by the fact that the sun has been above the horizon since dawn, and the fact that we are taking advantage of this strong angle of incidence on a steeply sloping land surface. So we can actually map something called slope aspect. Slope aspect is the direction that a slope faces on something called a digital elevation model. We haven't talked about those too much in the class yet, but in the last exercise, you'll be working using a digital elevation model to actually map slope aspect. And the map in the upper left represents a slope aspect map where in this case, you have to remember that north is down. And so consequently, the slopes that are colored red or yellow are north-facing slopes or northeasterly facing slopes, whereas the slopes that are colored in the blues are south-facing or southwesterly facing slopes. So we can begin to talk about the angle that the aspect of these slopes and how that aspect is going to affect the temperature regime on the slope itself. And what I've drawn on this aspect map, I've drawn the ridges, the topographic ridges, the tops of the ridges, so that you can begin to get a sense of this north-facing slope here, the south-facing slope, the south-facing slope, the north-facing slope, the south-facing slope, the north-facing slope, and so on. And you can see that really nicely in the two slides to the right of the DEM, where we can see the southerly aspect of the unvegetated slope and the northerly aspect of the vegetated slope, and a close-up of the image is shown in the bottom. The southerly aspect then is drier, it's warmer, and as a result, the vegetative cover is more brushland and grassland vegetation, whereas the north-facing slope with a northerly aspect is more moist, it's cooler, and consequently it has a lusher woody vegetation. Prevailing wind patterns are important, and this diagram shows what's called a wind rose for Minneapolis-St. Paul Airport over the course of the 2018 calendar year. And a wind compass talks about compass direction from which the wind is blowing. So we can talk about the wind blowing from the northwest, the wind blowing from the north, the wind blowing from the east, from the southeast, from the south, and so on. So the first component of a wind rose is the compass direction from which the wind is blowing. The second component is the wind speed, how fast is the wind blowing. And third is frequency, with which the wind speed and direction occurs over time. So we can see in Minnesota then, at least for the year 2018, that the prevailing wind patterns tended to be northwesterly and southeasterly. That is to say, we had a much greater percentage of time during which the wind was blowing from the northwest and blowing from the southeast. Then we had secondary peaks in the north to northeasterly quadrant and in the west southwesterly quadrant. St. David in 1974 made the observation that the shining sun giveth heat and the blowing wind taketh heat away. So we can begin to talk about integrating the concept of the wind rose into our assessment of slope aspect, begin to talk about the composite effects of wind and slope aspect on temperature. We'll talk more about that in just a minute, but this slide nicely illustrates that, because we can see this south-facing slope, very direct angle of incidence with the sun, occurring during a period of time during the day when the sun has been in the atmosphere, the sky, for quite some period of time. We have a fairly perpendicular angle of incidence for the red structure, and so we can talk about this slope having a fairly high incidence of solar radiation, whereas the lower positioned, the orange structure is positioned further down on the slope where the angle of incidence is more acute. The angle of incidence between the sun's rays and the surface of the earth is more acute here than it is here. So the red structure is going to be warmer simply because of its position on the slope, the steepness of the slope, and the angle of incidence. And then when we get on to the north side of the slope, we can begin to talk about the impact of blowing wind. The blowing wind taketh heat away. And here the cold winter wind coming out of the northwest, north-northwest, west-northwest is going to be impacting the upper slope more so than the lower slope, And so this blue structure then will have the coldest effects of wind and the coldest effects of sun because it's on the north facing slope and it's directly impacted by the cold winter winds. So we can combine the notion of slope aspect and steepness with the notion of compass rose to begin to characterize a broader perspective on temperature conditions in the landscape. This slide actually shows the study area where in fact aspect has been mapped and combined with wind conditions. And so we can talk about these south facing slopes being the warmest slopes, the kind of honey-colored slopes being second warmest, the orange slopes being third warmest, and so on until we get into the cooler slopes. So this begins to give us a sense by integrating temperature conditions associated with wind with temperature conditions associated with slope aspect and steepness of the microclimatic conditions that are going to exist in the landscape. In the last part of the lecture, I want to talk about access to development and transportation infrastructure as a basis for suitability assessment. And then I want to try to apply these concepts to the Lake Town Township study area, producing maps similar to what you'll be producing in the exercise. The first concept is proximity to existing development. The idea here is that proximity to existing development and infrastructure is desirable. Why is it desirable? Because it costs a lot of money to run sewer pipes, and it costs a lot of money to run roads out to remote locations. And so the closer existing infrastructure, whether it be development infrastructure or transportation infrastructure, is to an area that's going to be developed, the lower the public and private costs are. So the principle is close but not too close, because obviously nobody wants to live along Interstate 94. So this map begins to show the proximity of the landscape to existing development patterns. And the purple areas represent those areas that essentially have already been urbanized in our study area. And then I've simply buffered out a certain distance to come up with a relative ratio, a relative measure of the proximity to existing infrastructure, wherein the dark green and the medium, the Kelly green, are better suited for future development than is true of the yellow or the orange conditions. Here we can talk about proximity to county highways, looking at the county highways, mapping distant zones from the county highways, and coming up with a variable that describes proximity to county highways ranging from 10 to 6, where the 10s are those land areas that are in closest proximity to the county highways, and the reds are the areas that are most distant. We can take the same concept and apply it to Minnesota trunk highways, apply it to the US trunk highways, and then we can take all of that and smush it together and begin to come up with raw proximity to infrastructure, whether that infrastructure is development infrastructure or transportation infrastructure, and simplify that map so we can really begin to talk about the suitability of the landscape for different kinds of development based upon its proximity and access to existing transportation and development infrastructure. This map, again, is the map I showed just a minute ago. It talks about in the study area microclimatic conditions associated with slope aspect and wind direction. Here we're looking at soil suitability for dwellings and characterizing it in terms of very limited, somewhat limited, and not limited. These measures are coming right straight out of the Soil Survey Manual. There are criteria in the manual that identify soil suitability for dwellings as evaluated by soil scientists that look at a composite of soil texture, soil structure, soil moisture level to come up with a composite suitability rating. At first for dwellings overall, related to things like suitability for foundations, etc. And then we can talk about suitability for septic tank drain fields. And again, looking at depths to water table, soil texture and structure, and so on. And so we can begin to use these maps to begin to locate areas that are going to be more suitable for future development based upon soil characteristics. Here we're talking about suitability of development based upon slope steepness. And we can simplify this into three classes where the red areas, either because they are water, lakes, you may recognize Lake Waconia in the upper left-hand corner, or because they are on steep slopes, which you may recognize down along the Minnesota River Valley. Then the yellow areas are somewhat limited by steepness, and the green areas are not limited by steepness. So what this map is telling us is that from the standpoint of slope steepness, these green areas are the most suitable for future development. If we back up to these maps, we can begin to see that we have good suitability down in the southern part of the study area based upon slope steepness and low. Lo and behold, we also have pretty good suitability from the standpoint of suitability for septic tank drain fields. So we can begin to stack these different suitability maps on top of one another, begin to look through the maps, gain some sense of composite suitability for future development patterns. Here we see suitability based upon flood hazards. And here we see suitability based upon solar aspect. And this map takes into account both slope aspect as well as wind conditions. So all of these maps then can be used as a basis for beginning to identify the suitability of the landscape for different kinds of uses. And if you set up a program of uses, what are the different kinds of uses we're trying to put into the landscape? Begin to think about what kinds of biophysical conditions are needed to support that particular kind of use. Then if we can map those conditions, we can actually begin to identify areas based upon combined factors that are going to be most suitable for different kinds of development patterns. Thank you very much.